Welcome to the 2021 Senior Design Expo. We're the Snow Accumulation Measurement System team, otherwise known as the SAMS team. We were enlisted and sponsored by the National Center for Atmospheric Research to find a cost-effective way to measure snowpack in hard-to-reach places in the mountains. NCAR wanted us to tackle this project because their current methods for measuring snowpack are not as efficient as they would like. They currently use a combined approach between a manned fixed-wing beach propeller aircraft equipped with a spectrometer and Regal LiDAR sensor to measure and analyze the snowpack, and a system known as SNOWTEL. This is an array of sensors that measure atmospheric data, depth, mass, and snow water equivalent of the accumulated snowpack in remote areas. Neither of these methods are their ideal systems, as manned flight hours are wildly expensive, upwards of hundreds of thousands of dollars per year, and the SNOWTEL sites do not provide coverage or data across large areas. When asked about what cost-effective meant for NCAR, they gave us a wide-ranging budget, saying the relative cost of the manned flight hours make nearly anything cost-effective for them. We explored multiple solutions, including an RF antenna, an analysis system, simple ground-based sensors, and 3D imagery techniques to measure this changing environment. After multiple iterations of various prototypes and a proof of concept using an RGBD camera, similar to the technology of LiDAR, we decided the 3D mapping solution was the most viable, both in effectiveness and fitting within budgetary constraints. Our budget for this project was a total of $1,600 over 2 semesters, including all costs for R&D along the way. We came in under budget, with some of the purchases not making it into the final design. Our final product would cost around $200 less than our total spend over the project's lifetime. Most of this was spent in computing and sensor hardware, with the Jetson Xavier and LiDAR sensor being the largest spend categories. The solution we present uses multiple hardware and software systems. Our hardware consists of an NVIDIA Jetson Xavier, LiveVox Mid-40 LiDAR sensor, servo motors, and an Arduino Uno. Our software is wide and varied as well. We use Python, Ubuntu, Robot Operating System, Open3D, NumPy, and Jupyter Notebooks for various systems and applications. Pictured here is a block diagram of all major components of SAMS. The dotted outline represents the housing box referenced earlier. All connections are color-coded according to the legend shown. We utilized I2C, USB, Ethernet, and Wi-Fi connections to connect all the individual systems. The current prototype uses a camera tripod to hold all the components. The LiveVox Mid-40 LiDAR is connected to the custom servo mount, which is attached to the top of the tripod. The remaining components are all housed within an 8x8x4-inch junction box mounted to the tripod's vertical pole. This simple integration allowed us to conduct tests with ease, consolidating all the components into an easy-to-transport unit. The entire mapping process was automated by the SAMS team. The software for this consisted of 4 separate scripts, a main Python script, 2 Bash, and a C++. The Python script is called to run the entire mapping process. It starts by creating a system timestamp when the process begins. A new folder is created in the SAMS directory, named with this timestamp. Next, the script creates 2 subprocesses, one for each ROS node. The 2 ROS nodes are used to interface with the LiDAR sensor as well as create live 3D maps. Once both the mapping and driver systems are running, Python sends a signal from the Xavier's I2C bus to the Uno servo shield combination. Once received, the Uno initiates a function that rotates the LiDAR gradually through its field of view. The servo system then moves through its total field of view of 180 degrees horizontal and 50 degrees vertical, moving in single-degree increments to create smooth movement. Throughout this process, the Xavier and Arduino are communicating to establish when the process is complete. Once the Uno is done moving through its entire range of motion, the Xavier shuts down the 2 running ROS nodes, saves 3 output files, and resets the servo mount to the new starting position. The LiDAR sensor works by moving a small laser around in a flower-style pattern very quickly. The sensor then times the difference between when the laser is shown and when it receives the reflection of that signal. This time-of-flight paradigm allows the sensor to move very quickly and create 3D measurements of its environment with 2 centimeter accuracy and distance calculations. The LiveVox mapping software uses the SURF algorithm to stitch together these readings as the sensor moves around in an environment. This enables us to create highly detailed, accurate 3D maps of an area in real time and export this data for further calculations and processing. The output of this process is 3 distinct files. Each is a point cloud file type that stores the three-dimensional information about each point measured and the reflectivity of that point. Our first file is the corners file, which uses edge filtering to only store and log edge data. This file is the smallest of the bunch and stores important information of the environment's edges without planar points. The second is the surf file, which is a slightly larger file that has points that represent all planes and objects in the area. This map is useful for having more data while still being a smaller file size to simplify processing and computational time. Our final file is the all points file. This is the largest by far and stores every point measured during the mapping run. This is very useful as it has a very high resolution of the image of the environment and has more headroom for later downsampling, refinement, and processing. Two independently captured point clouds will tend to misalign in software due to variations in the mapping process as well as positional information from either GPS or IMU sensors. The Open3D Python library is used to accomplish all of the alignment and filtering tasks. To accurately measure the difference between the two pieces of data, they must be aligned so they accurately represent the 3D space compared to one another. We do this by using a multi-step process of downsampling the point cloud, removing ground points, and using RANSAC and ICP registration algorithms to statistically align the data. To start, we remove most of the points representing the ground and horizontal surfaces. When comparing a pre-snow image to a post-snow image, aligning can be difficult as the whole cloud could be shifted up and aligned expecting the ground to be on the same plane. Normal vectors are calculated for each of the points in the cloud and then filtered by a threshold value for their z component. If a normal vector has a large z component, it means that the point is on a plane facing up and therefore prone to collecting snow. After filtering both clouds for these z-facing normals, we further refine our alignment using the ICP method. The output of this process is a matrix of transformation values that can adjust the position of one cloud to match the other. This transformation matrix is then applied to the more data-rich all points clouds, which can be used for a much better calculation of difference between the two with a very high resolution of points. They are then downsampled slightly using voxel downsampling and outliers removed with the radius outlier method. This reduces the amount of points to process as well as increases the accuracy of the distance calculation by removing excessive information as well as noise from the data. The depth calculation is done by using Cloud Compare's M3C2 calculation, which computes the distance between two small planes created by sampling multiple points within a given radius. Once the process is complete, the output is a new point cloud where each point now represents a scalar value of the distance found from one to the next. This is then filtered to remove values less than 6 centimeters as there are many small differences found lower than this range due to mapping and sensor inconsistencies. The new dataset can then be colored to show extremes in the difference as shown here. Deep red represents the smallest changes and white represents the largest changes. The gaps in the cloud compared to the previous demonstrations are filtered out unimportant information such as structures, objects, and other areas that don't collect snow.